now I present to you the second presenter, so Pham. Again, I'll present her in French and then in English. So, Pham a obtenu un doctorat en recherche opérationnelle à KU Leuven, en Belgique, et a travaillé comme stagiaire postdoctoral à la même université avant de rejoindre Polytechnique Montréal en novembre 2020 sous la supervision du professeur Louis-Martin Rousseau. Pendant son doctorat, Pham a étudié les méthodes hybrides qui combinent des techniques provenant à la fois de l'intelligence artificielle et de la recherche opérationnelle. À Polytechnique Montréal, en tant que membre de Analogue, elle applique ses connaissances des méthodes hybrides pour optimiser la conception et la prestation de soins de santé. Elle a travaillé sur plusieurs projets visant à améliorer la qualité des soins dans des hôpitaux et centres de santé de Montréal au Canada. Ses recherches actuelles portent sur l'intégration des facteurs stochastiques dans la prise de décision en situation d'incertitude et leur application dans la prise de rendez-vous médicaux. After obtaining her PhD in operations research at KU Leuven in Belgium, Pham worked as a postdoctoral fellow at the same university before joining Polytechnique Montreal in 2020 under the supervision of Professor Louis-Martin Rousseau. During her PhD, Pham studied hybrid methods that combine techniques from both artificial intelligence and operations research. At Polytechnique Montreal, as a member of Analogue, she applies her knowledge of hybrid methods to optimize the design and delivery of healthcare. She has been working on multiple projects to improve the quality of care at several hospitals and health centers in Montreal, Canada. Her current research interest focuses on incorporating stochastic factors in decision-making under uncertainty and their applications in appointment scheduling. So we'll hear a bit about her recent work. So thank you, the floor is yours. And also you can use a printer if you like.
So hello everyone, and thank you very much for having me here, and thank you very much for the introductions. So today I would like to present our projects on a prediction-based approach for online dynamic patient scheduling. Thank you. So this was my first project as a postdoc at Polytechnique. And so I start. Okay. So if you live in Montreal and you ever need a doctor appointment, you would know that it's not really straightforward and it's quite painful actually. So just a quick Google search, I got a bunch of results about how broken the healthcare system in Canada is, how terrible the wait time, and how our healthcare workers are overworked and overwhelmed. So apparently the problem is not easy to fix, but we as operation researchers, we have to do what we do the best. That's, we want to optimize the use of the limited healthcare resources that we have to explore them to its full potentials. So that's what we as the Canada researcher in analytics and logistics in healthcare are striving to do. We want to optimize the treatment planning and the deliveries of healthcare. So when you do scheduling in healthcare, you have to deal with a high degree of uncertainties. There's uncertainty everywhere. For example, you have patient no-shows, cancellations with very often. You have deferrals in treatment plans. So is it normal that during the treatment, the patient would get worse or would get better, and you have to change the treatment plans? You have to do additional tests, for example, and you have uncertainty in resources, like the availability of some drugs, of some machine would be broken, and you have stochastic service times. Some procedures, some operations will take longer or shorter than planned. So when we do scheduling in healthcare, it's very important that we have to consider problems as dynamic problems in the rolling horizons, because new information, new arrival always arrive, and we have to take those into account. And is it very often in practice that we need to do online decisions? Of course, it makes more sense if we wait, let's say, until the end of the day to make decisions, because we will have more information and a larger space to make better decisions, better schedules. But in healthcare, it's quite complicated with a lot of operations constraints. So most hospitals and most healthcare centers, they require you to make online decisions, mean that when you receive a request, you have to make decision right away. Therefore, we have more constraints about running time. We have to make decisions fast, and we have like smaller search space. So it's important to take into account uncertainty. So in this talk, I'm going to talk about patient scheduling. In literature, usually patient scheduling are divided into allocation scheduling and appointment scheduling. So in allocation scheduling, is also referred as advanced scheduling. So let's say that we have a waiting list of patients and we have to schedule patients into calendars, meaning that we have to allocate the resources. So this patient will receive the service at this particular days. So that's one we call it advanced scheduling. So in allocation scheduling, the objective usually is to minimize the waiting times of patients, and we want to maximize the resource utilizations to maximize patient flow, for example. And the challenges in this scheduling is we have to deal with stochastic patient arrivals, and usually in different types, different urgency levels. And we have to deal with cancellations, for example. So a lot of uncertainty here. And then usually we divide it into two steps. We do allocation scheduling. So we have a set of patients that would receive service in a certain days. And on this day, we'll do appointment scheduling. This means that we will sequence patients receiving service in a day, and we give them the exact appointment times. So in appointment scheduling, the objective usually is to minimize the idle times of resources, like doctors or specialists don't have to wait too much for patients, and we want to maximize patient comfort. For example, like some of them want to come in the morning, some of them want to come in the afternoon, and if they have multiple appointments in the days, we don't want them to move too much or to wait too much between appointments. So the challenge in this scheduling is we have a lot of residence constraints between multiple resources. We have stochastic appointment durations. We also have deferrals, like some patients have to take some additional tests, for example. So in this talk, we focus on allocation scheduling. And we're going to use a case study of the radiotherapy treatments. And radiotherapy treatment is a type of therapy for cancer treatment. So cancer is a dangerous disease, and it's the second leading death worldwide. And in Canada, it's the first cause of death. And it's very challenging with a growing and aging population, because the number of elderly people in Canada have been double in the last 10 years and going to be triple in the next 10 years. So it will become more and more difficult to provide them with timely treatments. And to reduce death rates in cancers, we have two solutions. First, we need early detection. This is very important. And second, we need early treatments. Because in cancer treatments, the waiting times is also referred as killing time. So we don't want to wait the patient to wait for too long. So in these projects, we want to optimize the treatment scheduling of cancer patients to reduce their waiting time. So in cancer treatments, there are different ways to treat cancers, and usually different methods will be combined together. Amongst them, radiotherapy is the most popular, with 50% of cancer patients have to go to radiation therapies. So we want to optimize radiotherapy treatment schedules to reduce the wait and pay times. So as you can see on the slides, this machine is called linear accelerators, and this patient is receiving radiotherapy sections. So what the machine does is that it delivers a small dose of radiation to the tumor site to kill cancer cells. It has to be very precise because we don't want to kill healthy cells. And this small dose of radiation we call a fraction. And usually for our treatment plans, we have multiple consecutive fractions. This means that once the patient starts the treatment, it has to take place every day until the treatment plan is finished. And each patient, we have different fraction durations. So let's say that a patient needs 10 minutes sections. Another patient would require half hour, or some patient would require even 1 hour sections. And Linux is a very expensive machine, so we really want to optimize this. And so this problem is a patient scheduling problem with multi-appointments and multi-resources. Okay, so this project is a collaboration with SHAP, which is the Hospital of University of Montréal. SHAP is the largest cancer center in Quebec and one of the largest, not really, in Canada. But they have 10 machines, 10 Linux, 5 generous, and 4 specialized. And the last one is a special one, which is very, very precise. And they received, in 2019, they received 3,500 new patients. And this number, I don't have the exact number now, but it's increasing every year. And when I was working on these projects, I assume they still did scheduling manually with scheduling staff. But at the time, actually the project is collaboration with GRAY as well. And GRAY's Oncology is a startup spin-out from Hannah Lockley Research Share. And right now, GRAY has deployed their scheduling system as shown and from the beginning of this year. And this is being operating and under improving. And we are expanding the business to different hospitals in Quebec and in Canada as well. So it's very nice to see that actually that the algorithms are being applied in real life. Now, when in Quebec, cancer patients are divided into 4 categories that you see here. P1 and P2 are palliative patients. They are patients with in the final stage of cancer, so they are in intense pain and they need urgent treatment to relieve the pain. So the treatment deadline is 1 day or 3 days for P1 and P3. And for curative patients, without a patient that actually receive a treatment to cure cancer, they have more relaxing deadline, which is 40 days and 28 days after the treatment request. So as you can see on the slides that P2s, we have 30% of patients at P2, but 80% of them receive the treatments after their recommended deadlines. And we have 75% of P3 receive the treatment after their deadline as well. So apparently that now we are under capacities, and it's important to make the best use out of the resources. So for literature, because we study this problem, like we saw the problem dynamically and online as well, because so if the requirements from SHAP that they have to do online decisions, we schedule a patient one by one when we receive the request. So we review the literatures of the online dynamic problem only. So the literature is quite small for radiotherapies. And the main, there are 2 main approaches. The first one, they model the problems as a macro precision process and solve it as an approximately dynamic programming. So there are 4 papers in this approach. And then we have stochastic programming combined with online programming by Antoine Legrand. However, on those approaches, we have the same issues that we have in scaling issues. I think that the biggest instances that they can solve here is 3 Linux, and we have 8 Linux in real life assumed. So it's quite impossible to apply those to our problem. So what we want to do now, if you look at the slide, you will see that the allocation profiles assumed. We have different. We have 4 categories of patients. And we have, like, this is a portion of resources allocated for P3. And then we have a small fraction here for palliative patients. So let's say that, how do we schedule patients? When we receive a treatment request from P3 or P4, we have to schedule them, let's say 1 or 2 weeks in advance. How do we know that how much capacity should be reserved for for urgent patients because we have to schedule them 1 to 3 days starting from the request. So a very common solution in real life and in literature as well is that they would preserve a constant amount of enough capacity for palliative patients. However, when we look at here, for example, let's say that if we preserve that much of enough, like let's say 10%, then we waste some resources here for, and we waste some resources here like this section. So we have to delay curative patient for that. But if we research too little, let's say like 5%, then we have a part of palliative patient that we don't have enough capacity for that. Therefore, we want to build a prediction-based approach. It means that we're going to look at the allocation profiles of the problem, and dynamically we decide that how much should we delay the low priority patients. Now, before going to the prediction-based approach, I'm going to present some scheduling strategies. So first, batch scheduling. So batch scheduling, so let's say that we wait until the end of the week. This is like day 4, business days. And we have a batch of patients like arriving during the weeks, and we do scheduling decision right here. So, and for palliative patients, we always schedule at arrivals because they have to be treated urgently. We propose mixed integer programming for batch scheduling. I'm not going into details, but essentially we have a binary variable to assign a patient to a day and a Linux, and then we want to minimize the waiting time and the overdue time. So this is the constraints. And here we have offline scheduling. So offline scheduling means that we assume that we have perfect knowledge of future arrivals of patients, and then we schedule at once, like right here. But we know in advance that like which patient will be arriving which day. So the offline solutions is the perfect scenarios that we can have. And then we have online scheduling, which is the strategy that the approach that they are using as you know. So when a patient arrives, we will start, it depends on patient type. Let's say that we have a curative patient. So we will start looking at 2 weeks after the admission of day 0, we will start looking at day 10. And this patient requires 3 sections and 10 time slots each. So we will start looking here, and this is the capacities. We will see that we cannot schedule a patient to these days because the next day doesn't have enough capacities. So we will look ahead, and then we'll see that we can schedule a patient to this day, the first day after 2 weeks of admissions. So for online screening, we assign patient to the first eligible date. Now, for the prediction-based scheduling, it's quite similar, but instead of starting looking from a fixed date, we start looking from a predicted starting days given by regression models. So the question is that now, how we know a good starting date for a patient to start looking? Yeah, so that's how we do it. We train the regression models based on the offline solutions, really the perfect scenario that we can have. So we have a lot of problem instances, and then we solve the offline scheduling to get a bunch of offline solutions. And then from those bunch of offline solutions, we generate training data. The future of data would be like for each patient corresponds to trending observation. And the future is the patient's characteristics, like for example, the priority, the number of sections, the fraction durations. And then we also have the present allocation profiles at the institution. And then the labels of the data of the observation would be the patient waiting time in the offline solutions. And then we have that training data. We train the regression models, and these regression models will be used to predict the best starting date of a patient. So now let's look at the numerical results. To generate data, we generate patient arrivals following Poisson distribution. The treatment plans are taken from historical data. And Now I want to introduce the instant setting. So an instant setting in the number, BNAX, and arrival rate. So each instant setting corresponds to a particular hospital. So usually each hospital would have that fixed number of BNAX and would have that stable arrival rate with the average daily number of patients. And then for each patient setting, I generate 500 instances. 500 of them are used for training the regression models. Okay. Now to train the regression models, we try out different regression models, and then we decided to go with XGBoost because XGBoost got the best performance on the testing set, and on top of that, the training time is very fast. So to evaluate the approaches, we have 4 batch scheduling approaches and 2 online scheduling. So this is our prediction-based approach. We compare with offline scheduling and then the batch scheduling that we make decisions daily and weekly. And then we have a daily query as well. So to do the simulation, we have to know that for this number of BNAX, what is the suitable arrival rate? Because like if the arrival rate is too much for that number of BNAX, it doesn't make sense in practice. So we do choose capacity simulation. The first capacity simulation, we run the model with no capacity constraint, and then we measure, and then we plot the capacity, the occupancy of BNAX. So if you see that if this line is above the red line within the BNAX capacity, it means that this arrival rate is not really realistic for this instance. So you can see the arrival rate of 65 is not realistic for how many BNAX is this? Sorry, I didn't put, I think it's 4 BNAX. And then we have even the orange lines, we have a little bit like sometimes it's above the red line. And then we have the second capacity simulations where we have the capacity constraints, but we plot the waiting days of patients. And if the waiting days like goes up by 10, it means that it's not realistic. So those 2 simulations agree with each other that 6.5 is too much for BNAX. So we decided to test, I think that's 5 and 6, because we want to evaluate with different scenarios, like the same number of BNAX, but with a broadest scenario and a less broadest one, how the algorithm would perform. Now, we are looking at the results of BNAX. And we have the arrival rate of 5 and this the arrival rate of 6. So these are more crowded scenarios. So we see that for the arrival rate of 5 patients per day, we see that this is our approach on online prediction. We the waiting time and the overdue time of palliative patient B1 and B2 are lower compared to other approaches. So the first one is offline solution, which is the best scenario we can have. However, we can see that here we have in P4 we have more overdue times compared to other approaches. Now let's move on to a more crowded situation. We see that in more crowded situation, we see that the performance is really better in the online prediction, even for P3 and P4. We have like a little bit higher here, but the P4 in this trend is lower. So our conclusion that a more crowded hospitals, the better the prediction-based approach would perform. And now we move to 18 next, which is a really large hospitals. And we see that the differences is more significant here, especially in the crowded scenarios with really good performance in P1 and P2, and then we have P3 and P4 kind of comparable to other approaches. Now, this is on theories. Let's see in practice. We want to test it on a real patient flow. So this is the real patient flow as shown from 2019, 2018 to 2019. So this is the blue light is the real arrivals, and we have the average arrival in the last 10 days. Then you can see that in real life, the situation is not ideal. Even the arrival rate is not really stable. So we want to see how sensitive our approach to fluctuation in arrival rates. So because in real life they have 7 Linux operating 8 hours a day, we generated instances with 7 Linux operating 8 hours a day. So recall the SHAP has 10 Linux, but 3 of those would operate half-hour days, and 1 Linux would be specialized for some special patients. So we generate instances for 7 Linux, and the arrival rate of 10.1. So we take the average arrival rate of the first 3 months data. And this is the results. We can see that the prediction-based model, so this is the result that we want to look at. The waiting time for palliative patients and the overdue time for palliative patients are better than on other approaches significantly. Even though we have the overdue times for P3 is higher, but that's a number that we are willing to exchange because it's like only 1 day more than, but we reduce significantly the overdue time of palliative. So I'm going to move to the final results, which is some nice extra, because in healthcare, explainability and transparency in decision making is very important, because the decision is human related. So we have to be able to answer the questions like, why do we delay this patient? Or if we schedule this patient 1 or 2 days in advance, what would happen? And it's very important when it comes to practice implementing an algorithm as a hospitals. And in order to do that, we use the SHAP values, which represent the relative strength of variables on the outcome. This is what we use in machine learning. And if you look at this graph, actually it's kind of similar to the feature importance graph for decision trees, but this has more information. So this plot represents the shape of the data and the impact of each feature on the data, and also the direction of the impact. So if you look at this plot, you will see that the most important feature would be number of sections, and because it's on top of the plot. And then you see each data point, so each point on the graph represents an observation. And if the observations on this side, it means that it shifts the outcome of the model to the positive direction, it means that it increases the waiting time. And on data points over here, it increases the waiting times. And then we have the color of the data points from low to high. So the red data points mean that the number of sections is higher. So from this plot, we see that patients with a higher number of sections will be more likely to have more waiting times and viruses. And similarly, we can interpret with the delay. So apparently the patients with more lower priority, so they have higher due days, will have more waiting times. So this is the overall observation of the models, but we want to explain each decision. So this waterfall plot helps us to interpret an individual decisions. So how do we do that? This is a particular instance, and this is the values of features. So this patient is a P3 patient because the due date is 10, and this patient has 33 sections. And how do we read the plot? We start from the bottom, and these values is called the base values. In general, it's the average outcome of the whole training set. So the average values is the 23 days, and then we add up the values. So the red one is positive and the blue one is negative. So this is the contribution of each feature to the decision, and we go up to the final decision here. So this patient has waiting the times of 26 days, and number of sections has the most positive contribution to these decisions. So this is a nice way to explain the decisions that we make. Okay, so to conclude my post, my presentations, we propose a machine learning-based approach for an online dynamic patient scheduling, and the results shows that it works well on a large and growing hospitals, and it's not too sensitive with the fluctuation on arrival rates. And we also explain that how we support explainability in decision making. Thank you very much.